Every clear night, the Milky Way stretches across the sky like a quiet river of light. It looks peaceful, it looks safe. But 26,000 light years from where you are sitting, something is happening that most people will never emotionally accept. At the exact center of our galaxy, a supermassive black hole, 4 million times the mass of the Sun, is warping space, shredding stars, and driving flares so violent that they lit up surrounding gas clouds with the fury of 10,000 times its current brightness, possibly within the last few centuries. Stars orbit this monster at 8,000 kilometers per second. Magnetic fields twist into spirals at the edge of the event horizon. And in 2026, scientists confirmed it was far worse than anyone expected. If you enjoy journeys that change how you see the universe, consider tapping that like button and subscribing. It helps more than you might think, and it keeps stories like this one coming. Now, get yourself comfortable. Let's begin. Go outside on a clear night, far from any city, and look up. Wait for your eyes to adjust. After 15 or 20 minutes, the sky transforms. A pale glowing band stretches from horizon to horizon, soft and luminous, cutting across the darkness like a brushstroke left behind by something ancient and unhurried. That band is the Milky Way, our galaxy, our home. It contains somewhere between 200 billion and 400 billion stars, and from where you stand, it looks like the most peaceful thing in the universe. Gentle, quiet, eternal. You could stare at it for hours, and nothing about it would suggest danger. Nothing about it would suggest violence. Nothing about that calm river of light would ever hint that at its exact center, something is happening so extreme that most of the scientific community spent decades refusing to believe it was even possible. 26,000 light-years from Earth, hidden behind walls of gas and dust so thick that no optical telescope has ever seen through them, sits an object so massive that it bends the fabric of space-time into a gravitational pit from which nothing, not light, not matter, not information of any kind, can escape. That object is Sagittarius A star. It is the supermassive black hole at the center of our galaxy. It weighs approximately 4 million times the mass of the Sun, and what scientists have found in its immediate vicinity over the past 3 decades has progressively demolished everything we thought we understood about what the heart of the Milky Way looks like. This is not a story about some distant, exotic system billions of light years away. This is about the galaxy you live in right now, the galaxy whose stars you can see tonight. The galaxy that from every angle appears quiet and ordinary and safe. The shock is not that strange things happen near black holes. The shock is that this particular black hole is ours, and what surrounds it is already far more violent, far more active, and far more hostile than most people have ever been told. To understand why the discoveries near Sagittarius A star are so hard to accept, you first need to understand how thoroughly the Milky Way disguises its own center. The galactic core lies in the direction of the constellation Sagittarius, roughly toward the southern sky for observers in the northern hemisphere. If you could strip away every obstruction, you would be looking at the densest concentration of stars, gas, radiation, and gravitational energy in our entire galaxy. But you cannot strip away those obstructions. Between Earth and the galactic center stretches an enormous volume of interstellar dust and molecular gas that absorbs visible light almost completely. For every photon of visible light that leaves the galactic center heading toward Earth, the dust blocks it. The center is invisible, not dim, not faded. Invisible. If you relied only on human eyes and optical telescopes, you would never know the galactic center existed at all. You would see the Milky Way as a glowing band of nearby stars, and assume the whole galaxy was just more of the same, calm, scattered, unremarkable. This is exactly what happened for most of human history. For thousands of years, the Milky Way was poetry, mythology, a celestial decoration. The ancient Greeks called it Galaxias, the Milky Circle. Various cultures saw it as a river, a road, a trail of spilled grain. Even after Galileo pointed his telescope at the band in 1610 and resolved it into individual stars, the center remained hidden. Nobody knew a center existed. Nobody suspected what it contained. The galaxy was simply a vast collection of stars with no obvious core, no engine, no beating heart. That began to change in the 1930s, when Carl Jansky, a radio engineer working for Bell Telephone Laboratories, detected a persistent source of radio static coming from the direction of Sagittarius. Jansky was not looking for cosmic signals. He was trying to identify sources of interference in transatlantic telephone communication, but the signal he found did not match any terrestrial source. It peaked once per day, drifting with the stars, pointing directly at the center of the Milky Way. Jansky had stumbled upon the first detection of radio emission from the galactic core. The discovery was published, noted with curiosity, and largely ignored. The world was heading toward a war, and nobody knew what to do with cosmic radio static. It took another 40 years before anyone figured out what was actually producing that signal. In 1974, astronomers Bruce Ballack and Robert Brown used the Green Bank Interferometer in West Virginia to observe the galactic center at radio wavelengths. They discovered an extremely compact, extremely bright radio source sitting at the precise gravitational center of the Milky Way. The source was tiny by astronomical standards, far smaller than the surrounding star clusters and gas clouds, yet it radiated intensely. Brown later named it Sagittarius A star, with the asterisk denoting its exciting or special nature. At the time, no one could prove what it was. The object was simply catalogued as an unusual compact radio source and filed alongside hundreds of other unexplained astronomical detections. But something about Sagittarius A star refused to stay filed away. Throughout the 1980s and 90s, as radio and infrared telescope technology improved, astronomers kept returning to the galactic center and finding things that made no sense under ordinary stellar physics. The region around Sagittarius A star was strange, not subtly strange, fundamentally strange. Infrared observations revealed a dense cluster of massive stars swarming within just a few light years of the radio source. Gas clouds in the vicinity showed extreme velocities, as though something was stirring the surrounding material with tremendous gravitational force. X-ray telescopes detected high-energy emission from the region, consistent with superheated matter being accelerated to enormous speeds. Every new observation hinted at the same conclusion, but it was a conclusion that the scientific community approached with extraordinary caution. The idea that a supermassive black hole might sit at the center of the Milky Way had been proposed theoretically as early as 1971, when Donald Lyndon Bell and Martin Rees argued that many galaxies, including our own, could harbor massive black holes at their cores. But proposing the idea and proving it were entirely different things. Black holes, by definition, cannot be seen directly. They emit no light. They produce no signal that you can point to and say, that is the black hole. You can only infer their existence through the behavior of matter around them. And inferring the existence of an object 4 million times the mass of the Sun, hidden behind 26,000 light-years of obscuring dust, required evidence so overwhelming that no alternative explanation could survive. That evidence came from 2 independent research teams working in parallel for over a decade. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at the University of California, Los Angeles. Both teams used the most powerful infrared telescopes available, the European Southern Observatory's Very Large Telescope in Chile and the Keck Observatory in Hawaii, to peer through the dust and track the motions of individual stars in the immediate vicinity of Sagittarius A star. They were not looking at the black hole, they were looking at the stars around it, watching them move, year after year, orbit after orbit, and using those motions to calculate the mass of whatever was pulling on them. What they found was astonishing. Stars near the galactic center were not drifting lazily through space, the way stars in our neighborhood do. They were racing. A star designated Stu was clocked completing a full orbit around Sagittarius A star in just 16 years, reaching speeds exceeding 25 million kilometers per hour at its closest approach. That is roughly 2.5% of the speed of light. Another star, Sohn, followed a different but equally extreme orbital path. Each star they tracked told the same story. Something at the center of this cluster was exerting a gravitational pull so immense that it could whip full-size stars around like stones in a slingshot. By combining the orbital data from multiple stars, both teams independently calculated the mass of the central object. The answers converged with remarkable precision. Approximately 4 million solar masses compressed into a region smaller than our solar system. There is no known physical object other than a black hole that can pack that much mass into that little space. A star cluster of that mass would be visible. A dense cloud of gas would disperse. A concentration of dark matter would not produce the observed radio and X-ray emissions. Every alternative was tested, debated, and ruled out. The conclusion was inescapable. Sagittarius A star is a supermassive black hole. In 2020, Genzel and Ghez were awarded the Nobel Prize in Physics for this discovery. The citation specifically recognized their work in demonstrating that a supermassive compact object governs the orbits of stars at the center of the Milky Way. It was one of the most important confirmations in the history of astrophysics. And yet, for all its significance, the discovery of the black hole itself was just the beginning. Because the truly unsettling findings were not about the black hole, they were about what exists near it. To appreciate why those findings matter, you need to understand what near Sagittarius A star actually means in physical terms. The galactic center is not a point, it is a region. Within a few light years of the supermassive black hole lies one of the most extreme environments in the observable universe. Star densities in this region are millions of times higher than in our solar neighborhood. Where the Sun's nearest stellar neighbor sits over 4 light-years away, stars in the galactic center can be separated by distances comparable to the size of our solar system itself. The gravitational field is dominated entirely by the black hole. Tidal forces stretch and compress matter across gradients so steep that the difference in gravitational pull between the near side and far side of an orbiting object can be enormous. Radiation floods the region from every direction, produced by hot gas spiraling inward, by colliding stellar winds, by shock waves from supernovae, and by the flaring activity of the black hole itself. This is not a place that resembles anything in human experience. It is not even a place that resembles most of space. The vast majority of the Milky Way is calm, cold, and empty. Stars drift through near vacuum at modest speeds, separated by light-years of nothing. Planets orbit in stable, predictable paths. The interstellar medium is thin, quiet, unremarkable. That is the galaxy you see when you look at the night sky. That is the galaxy every textbook describes. But the galactic center operates under entirely different rules. Gravity is not a gentle background force there. It is the dominant feature of the landscape. Everything that enters this region, every star, every gas cloud, every photon, is caught in a gravitational environment so intense that the normal assumptions of astronomy simply stop working. The observational difficulty of studying this region cannot be overstated. Sagittarius A star lies behind the thickest part of the galactic dust lane. Visible light from the center is attenuated by a factor of roughly 1 trillion. If the galactic center were as bright as the full moon in visible light, the dust would reduce it to invisibility. Only wavelengths that can penetrate or bypass the dust allow observation. Infrared light, which has longer wavelengths than visible light, can partially penetrate the dust. Radio waves pass through almost unaffected. X-rays and gamma rays carry information about the highest energy processes, but require space-based telescopes because Earth's atmosphere absorbs them. Each observational window reveals a different layer of the galactic center environment, and no single telescope can see the full picture. This is why it took so long for the true nature of the galactic center to emerge. Scientists were not slow or negligent. They were working with fragmentary evidence, collected through narrow observational windows, filtered through 26,000 light-years of intervening material, and interpreted against the background of a theoretical framework that was itself still evolving. The idea that a galaxy could contain a supermassive black hole was radical for much of the 20th century. The idea that our galaxy contained one was even more unsettling, because it meant the peaceful Milky Way overhead was not what it appeared to be. The first major crack in the calm facade came from the infrared surveys of the 1990s. When astronomers finally had telescopes sensitive enough to resolve individual stars near Sagittarius A star in the infrared, they found a population of young, massive, luminous stars crowded within the central parsec, a volume roughly 3 light-years across. This was baffling. Massive stars are short-lived, burning through their nuclear fuel in just a few million years. Their presence near the galactic center meant they had formed recently, cosmologically speaking. But standard models of star formation said this should be impossible. The tidal forces from the supermassive black hole should shred any molecular cloud before it can collapse into stars. The gravitational shear should prevent the kind of slow, steady contraction that forms stellar nurseries. Yet, there the stars were, young, bright, and inexplicably close to one of the most disruptive gravitational sources in the galaxy. This became known as the paradox of youth. It remains only partially resolved. Some researchers propose that stars formed farther out and migrated inward through complex gravitational interactions. Others suggest that unusually dense gas disks near the black hole could overcome tidal disruption and fragment into stars. Neither explanation is fully satisfying. The young stars exist, and their existence tells us something uncomfortable about the galactic center. It does not follow the rules we derived from studying calmer parts of the universe. The paradox deepened as infrared monitoring continued through the 2000s. Astronomers began tracking not just the positions of galactic center stars, but their full 3-dimensional velocities, using a combination of radial velocity measurements from spectroscopy and proper motion tracking from repeated imaging. The picture that emerged was kinematic chaos. Stars moved on wildly different orbits, some nearly circular, others plunging on elongated ellipses that brought them perilously close to the black hole before flinging them back outward. The velocity dispersions were enormous. Individual stars reached speeds that would be considered extreme in any other astrophysical context, and the gas was even worse. Molecular clouds and ionized gas streamers near the galactic center showed velocities and turbulence far exceeding anything found in the galactic disk. The circumnuclear disk, a ring of dense molecular gas orbiting a few light-years from Sagittarius A star, rotates at speeds consistent with the black hole's gravitational influence, but also displays violent internal motions suggesting ongoing shocks and collisions. Ionized gas filaments called the mini-spiral thread through the central cavity, tracing paths that appear to be feeding material toward the black hole. The entire region is in constant, energetic motion. Then came the flares. Sagittarius A star had always been classified as an unusually quiet, supermassive black hole, compared to the blazing active galactic nuclei in other galaxies, which can outshine their entire host galaxy. Sagittarius A star emits at less than 100 millionth of its theoretical maximum luminosity. It is, by supermassive black hole standards, barely awake, but even a drowsy monster twitches. Beginning in the early 2000s, X-ray telescopes like NASA's Chandra X-ray Observatory detected sporadic but intense flares from Sagittarius A star. These flares lasted anywhere from a few minutes to a few hours, during which the black hole's X-ray brightness increased by factors of 10 to 100 or more. Infrared telescopes detected simultaneous or near-simultaneous flares in the near-infrared, suggesting that the same physical event was producing emission across multiple wavelengths. The flares were not coming from the black hole itself. Nothing escapes a black hole. They were coming from the hot, magnetized gas in the accretion flow just outside the event horizon. The leading explanation involves magnetic reconnection, a process in which tangled magnetic field lines in the superheated plasma snap and reconnect, releasing enormous bursts of energy in the process. This is the same basic mechanism that produces solar flares on our Sun, but amplified to an incomprehensible degree by the extreme gravitational and magnetic environment near a supermassive black hole. The temperatures in the flaring regions likely reach tens of billions of degrees. Particles are accelerated to relativistic speeds. The energy released in a single flare can exceed the total output of 100 Sun-like stars combined, concentrated into a region smaller than our solar system. These flares told scientists something important. Sagittarius A star may be quiet compared to other supermassive black holes, but it is not dormant. Its immediate environment is dynamic, unstable, and capable of producing sudden violent outbursts that inject massive amounts of energy into the surrounding region. The calm reputation was misleading. It was not calm. It was merely dim by the standards of objects that can outshine entire galaxies. By any terrestrial or stellar standard, The region around Sagittarius A star was a furnace of radiation and gravitational violence. By the 2010s, a clearer picture of the galactic center was taking shape, and it was a picture that clashed violently with the serene image of the Milky Way overhead. At the center of our galaxy sat a supermassive black hole with a mass of 4 million suns. Around it orbited a cluster of stars moving at thousands of kilometers per second on chaotic extreme orbits. Young stars existed where they should not be able to form. Gas clouds spiraled inward through a turbulent, magnetized medium. Flares erupted unpredictably, signaling violent magnetic events in the superheated accretion flow. Tidal forces strong enough to tear stars apart dominated the gravitational landscape. And all of this was happening just 26,000 light-years away, inside the same galaxy that looks like a quiet brushstroke of light on a summer night. But the story was about to escalate dramatically. In 2022, a global network of radio telescopes achieved something that had been considered impossible for most of the history of astronomy. They took a picture, not of a distant quasar, not of a faraway galaxy. They took a picture of the shadow of the supermassive black hole at the center of our own Milky Way. And what that image revealed, combined with what followed in 2024 and 2026, would push the galactic center from an extreme but manageable scientific subject into something that genuinely challenges how we think about the galaxy we call home. The observations were about to turn the theoretical into the visible, the inferred into the confirmed, the uncomfortable suspicion into an undeniable confrontation with a reality that most people, even most astronomers, had not fully internalized. The center of the Milky Way was not just hosting a black hole. It was hosting an environment so extreme that every new instrument pointed at it revealed something harder to accept than the last. What they found, when they finally looked closely enough, changed everything. On May 12, 2022, at coordinated press conferences held simultaneously in cities around the world, the Event Horizon Telescope collaboration released an image that no previous generation of scientists had ever believed they would see. It was not a photograph in the conventional sense. It was a reconstruction, painstakingly assembled from petabytes of radio data collected by 8 telescopes scattered across 4 continents, and the South Pole, all pointed at the same target during a narrow observation window in April of 2017. The telescopes had been linked together through a technique called very long baseline interferometry, which effectively turned the entire planet into a single radio dish the size of Earth. That planetary-scale instrument had been aimed at the center of the Milky Way, and what it captured was the shadow of Sagittarius A star. The image showed a glowing ring of superheated gas surrounding a dark central region. The ring measured approximately 52 microarc seconds across. To appreciate how small that is, imagine placing an orange on the surface of the moon and trying to see it from Earth. That is roughly the angular size the Event Horizon Telescope had to resolve. The bright ring corresponded to radio emission from plasma orbiting just outside the event horizon at speeds approaching the speed of light. The dark interior was not the black hole itself, because no instrument can image something that emits no light, but its shadow, the region where the black hole's gravity was so extreme that photons could not escape or were bent away from our line of sight. The diameter of that shadow was consistent with theoretical predictions for a Kerr black hole of approximately 4 million solar masses located at a distance of roughly 26,000 light-years. This was the first direct visual evidence of a supermassive black hole at the center of our galaxy. For decades, the existence of Sagittarius A star had been inferred from the orbits of stars, from radio emission, from X-ray flares. Every piece of indirect evidence pointed to the same conclusion. But seeing the shadow, seeing the ring of light bent around an object so dense that space-time closes in on itself, transformed the abstract into the visceral. The Milky Way was no longer a galaxy that probably contained a supermassive black hole based on strong circumstantial evidence. It was a galaxy where the black hole had been directly observed, its gravitational imprint stamped into the light of the matter swirling around it. But the image almost did not happen. Of the 2 black holes the Event Horizon Telescope had targeted, the other being the vastly more massive black hole in the galaxy, Messier 87, Sagittarius A star proved far more difficult to image. The reason was its size, or rather the consequence of its size for how fast things move near it. M87's black hole has a mass of roughly 6.5 billion solar masses, gas orbiting near its event horizon takes days to weeks to complete a single circuit. During the hours-long observation windows that the Event Horizon Telescope requires to gather sufficient data, the structure of M87's accretion flow remained relatively stable. Sagittarius A star is over 1,000 times less massive. Gas orbiting near its event horizon completes a full loop in mere minutes. This meant that the source was changing, even as the telescopes were recording it, like trying to photograph a child who refuses to sit still, except the child is a maelstrom of plasma moving at a significant fraction of light speed. This difficulty was not merely a technical inconvenience, it was itself a revelation. The fact that the accretion environment around Sagittarius A star changed on timescales of minutes told scientists something profound about the physical conditions at the event horizon. The plasma orbiting this black hole was not a stable, slowly evolving structure. It was a seething, turbulent system, reconfiguring itself faster than any accretion flow around a more massive black hole could. Each minute brought a new arrangement of bright spots, magnetic hotspots, and density fluctuations in the gas. The data recorded across a single night of observation contained not one image but hundreds of overlapping configurations, superimposed and blurred together by the time it took light to travel from the galactic center to the telescopes on Earth. The very speed of the accretion flow was erasing its own portrait as fast as the instruments could record it. To compensate, the collaboration employed computational methods that generated thousands of possible images consistent with the data, then averaged them to extract the features that appeared most consistently across all reconstructions. The resulting image could be grouped into 4 representative morphologies, all of which showed the same fundamental structure: a bright, thick ring with a comparatively dim interior. The ring was not uniformly bright, it displayed modest asymmetry, with one side slightly brighter than the other, consistent with relativistic effects, where gas moving toward the observer appears brighter due to Doppler boosting. The 4 morphological clusters differed in the precise distribution of brightness around the ring, with some showing a single bright concentration and others displaying a more distributed glow. But the ring itself, and the dark shadow it enclosed, appeared in every reconstruction. The underlying structure was robust despite the variability of the source. This variability also meant that the Event Horizon Telescope had, inadvertently, captured evidence of real-time physical processes occurring at the edge of the event horizon. Some of the brightness variations between different morphological clusters corresponded to orbital timescales of the innermost gas, suggesting that the imaging pipeline had frozen snapshots of plasma hotspots completing partial orbits around the black hole during the observation window. The Event Horizon Telescope had not merely photographed the shadow, it had recorded the accretion flow in motion, catching the restless churn of superheated matter circling a gravitational abyss at a significant fraction of the speed of light. The theoretical framework matched, the mass matched, the diameter matched. Every test the collaboration could devise confirmed that what they were seeing was the shadow of a 4 million solar mass black hole, our black hole, and the image itself was a testament to how violently active the environment around it remained, even during what we consider a quiet epoch. The image was a triumph, but it was also a doorway, because the same data that produced the shadow also carried information about the magnetic environment surrounding the black hole, and when the collaboration extracted that information 2 years later, the result was even more disturbing. In March of 2024, the Event Horizon Telescope collaboration released a new version of the Sagittarius A star image. This one was captured in polarized light. Polarization occurs when electromagnetic waves oscillate preferentially in a particular direction, and in astrophysics, polarized light is a direct tracer of magnetic fields. By analyzing how the radio emission from the accretion flow around Sagittarius A star was polarized, the team could map the structure and orientation of magnetic fields at the very edge of the event horizon. What they found was striking. The magnetic fields around Sagittarius A star were not chaotic or disordered. They were strong, organized, and spiraling. The field lines twisted in coherent patterns around the black hole, tracing a configuration that immediately reminded researchers of something they had already seen. When the same polarization analysis had been applied to M87's black hole, it had revealed nearly identical magnetic field geometry. The similarity was remarkable because the two black holes differ in mass by a factor of more than 1,500. M87's black hole is a colossus that is about as one of the most energetic jets in the observable universe, a beam of relativistic plasma extending 5,000 light-years into intergalactic space. Sagittarius A star shows no such jet, or at least it shows no jet that anyone has detected yet, but the magnetic field structure suggested that the machinery for producing a jet might be in place. This raised an unsettling possibility. If Sagittarius A star's magnetic fields look like those of a black hole known to produce a powerful relativistic jet, then either our black hole once had a jet, could have one again, or might even harbour a faint, hidden jet that current instruments cannot resolve. Any of those possibilities implies that the central engine of our galaxy is more active and more capable of violent energy output than its current quiet state suggests. The magnetic architecture is there. The infrastructure for extreme outbursts is built into the very structure of the accretion flow. Sagittarius A star is not a retired engine. It is an engine idling, with the ignition still connected. But the Event Horizon Telescope findings, as revolutionary as they were, captured only a single snapshot in time. They told scientists what the accretion flow looked like during one particular observation window in 2017. To understand whether Sagittarius A star had always been this quiet, or whether its subdued state was temporary, astronomers needed a way to look backward in time, not billions of years into the distant past, but centuries. They needed a cosmic time machine that could replay the black hole's recent history. In January of 2026, they got one. Researchers at Michigan State University, working with an international team and using data from the XRISM space telescope, published findings that fundamentally changed the narrative around Sagittarius A star. XRISM, a joint mission of NASA, the European Space Agency, and the Japan Aerospace Exploration Agency, had been launched in September of 2023. Its defining capability was spectral resolution, the ability to measure the energy of individual X-ray photons with a precision of roughly 1 part in 1,000. Previous X-ray telescopes could detect photons from the galactic center. XRISM could dissect them, reading their energies with the finesse of a laboratory instrument rather than a blunt astronomical detector. Earlier instruments managed spectral precision of perhaps 1 part in 10 or 1 part in 100. XRISM surpassed them by an order of magnitude, opening a window into the fine structure of X-ray emission that had been permanently blurred by the limitations of previous technology. The team pointed XRISM at a giant molecular cloud near the galactic center. Molecular clouds are dense accumulations of gas and dust, and several of them orbit within the central region of the Milky Way. Previous telescopes had detected faint X-ray emission from some of these clouds, and there had been long-standing debate about what was causing the glow. One hypothesis was that high-energy cosmic ray particles were exciting the cloud material. The other hypothesis was far more dramatic. The clouds were acting as cosmic mirrors, reflecting X-ray light from a past outburst of Sagittarius A star. The X-ray flash had long since faded at the source, but because the molecular clouds sat at different distances from the black hole, the reflected light reached Earth with a time delay, like an echo bouncing off a canyon wall centuries after the original shout. XRISM settled the debate. By analysing two extremely narrow ion emission lines in the X-ray spectrum of the cloud with unprecedented precision, the team determined the motion of the cloud and its spectral characteristics with enough detail to rule out cosmic ray excitation entirely. The glow was not being produced internally, it was a reflection. The cloud was echoing an X-ray outburst from Sagittarius A star that had occurred within the past few hundred to 1,000 years. And the brightness of that echo implied something staggering. At the time of the outburst, Sagittarius A star had been shining in X-rays at an intensity roughly 10,000 times greater than its current output. The brightest X-ray flare ever directly observed from the black hole, recorded in 2013, had reached only about 1% of this ancient outburst's implied brightness. The mechanism behind this cosmic time machine deserves closer examination, because it transforms the galactic center from a place we can only observe in its present state into a place whose recent history can be read from its surroundings. Imagine standing in a vast dark cathedral, You set off a flashbulb at the center. The light races outward in all directions. It hits the near wall first and bounces back to your eyes almost instantly. Then the far wall returns its echo a moment later. The side walls follow at intermediate delays. By watching the sequence of returning reflections, you can map the shape and distance of every surface in the room without ever seeing those surfaces directly. You are reading the architecture of the cathedral from the delayed echoes of a single flash. The molecular clouds around Sagittarius A star work the same way. Each cloud sits at a different distance from the black hole. When the black hole erupted, X-ray light travelled outward and struck each cloud at a different time. The clouds that were closest received the light first. Those farther away received it later. Each cloud then scattered a fraction of that light toward Earth. But because the geometry is three-dimensional, light that bounces off a cloud to reach us travels a longer total path than light coming directly from the source. The result is a time delay. A cloud sitting a certain distance from Sagittarius A star in the right geometric configuration might deliver its reflected echo to Earth decades or centuries after the original eruption faded at the source. By observing multiple clouds at different distances and positions relative to the black hole, astronomers can piece together a sequence of echoes from different moments in the eruption history. One cloud might be reflecting an outburst that occurred 800 years ago. Another might carry the signature of a separate event from 1200 years ago. A third might show the tail end of an eruption that happened just 300 years in the past. Each cloud is a frame in a slow-motion replay of the galactic center's violent history, and XRISM's spectral precision is the projector that makes the frames legible. The research team demonstrated that this approach is not merely theoretical, it is operational. They resolved the ion emission lines from the cloud with enough clarity to measure not just the brightness of the reflected signal, but the velocity of the cloud itself, confirming that the X-ray glow was geometrically consistent with reflection from the direction of Sagittarius A star and not from some other source. The implications were immediate and profound. Sagittarius A star was not merely a quiet black hole that occasionally twitched. It was a black hole with a documented history of violent eruptions so intense that their echoes are still visible today, bouncing off gas clouds scattered around the galactic center like flashbulbs reflecting off the walls of a darkened room. The black hole's current state of relative calm was not its defining characteristic. It was a temporary condition, possibly very temporary. The most recent major eruption could have occurred as recently as a few centuries ago, placing it within the span of recorded human history. Though the light from the event, originating 26,000 light-years away, would have taken that many years to reach Earth and would have been invisible to the naked eye regardless due to dust obscuration. The technique is still in its early stages, but the principle is established. XRISM has given scientists the ability to read the history of Sagittarius A star in the fading glow of its ancient tantrums. Future observations targeting additional molecular clouds at different positions around the galactic center will fill in more frames of this historical record, potentially revealing not just when outbursts occurred, but how long they lasted, how quickly they brightened and faded, and whether they followed any recognizable pattern. The galactic center may turn out to have a heartbeat, a rhythm of eruption and quiescence written in the reflected light of surrounding clouds, waiting to be read by instruments sensitive enough to decode the message. But even before XRISM revealed the ancient eruptions, scientists had already received a warning that Sagittarius A star's quiet reputation might be misleading. It came not from reflected echoes or theoretical models, but from a direct, real-time observation that briefly made researchers question whether their instruments were broken. On the night of May 13th, 2019, astronomers using the Keck Observatory in Hawaii pointed their infrared instruments at Sagittarius A star as part of routine monitoring that had been ongoing for more than 2 decades. What they saw was anything but routine. Over the course of roughly 2 hours, the black hole's near-infrared emission surged to approximately 75 times its typical faint baseline. It was the brightest near-infrared emission ever recorded from Sagittarius A star in the entire history of modern monitoring. The spike was so sudden and so far outside the normal range that the lead researcher, Tuan Do, at UCLA, initially suspected a calibration error. The telescope might be malfunctioning, the detector might be saturating, some instrumental artifact might be contaminating the data, but the signal was clean, the brightening was real. Sagittarius A star had done something it had never been seen to do before. The event was not a standard flare. Sagittarius A star had been monitored continuously in the near-infrared for over 2 decades, and during that time its emission typically varied by modest factors, flickering gently around a faint baseline. The 2019 event shattered that pattern. A factor of 75 above the quiescent near-infrared baseline placed it far beyond anything in the existing monitoring record, and in a category that existing models of the accretion flow struggled to explain. The brightening suggested either a sudden increase in the amount of material falling toward the event horizon or an unusually violent magnetic reconnection event in the inner accretion flow, or both simultaneously. Some researchers speculated that the passage of G2 through periaps 5 years earlier might have disturbed the accretion environment in ways that were only now manifesting as enhanced feeding. Others proposed that a clump of gas or a fragment of tidally disrupted material had fallen inward on a delayed trajectory, triggering a transient burst of accretion luminosity. No single explanation achieved consensus. The event remains incompletely understood, but its significance was not primarily about what caused it. Its significance was what it demonstrated about the nature of Sagittarius A star as an astrophysical object. For 2 decades, the monitoring record had shown a black hole that flickered modestly, producing small flares against a dim, steady background. The 2019 brightening shattered that baseline. It showed that Sagittarius A star was capable of producing infrared output far exceeding anything in the historical record, on timescales short enough to catch observers off guard. Without any obvious precursor or warning, the black hole's accretion environment was not merely variable. It was capable of extreme, unpredictable excursions that fell outside the statistical envelope of normal behavior. When combined with the XRISM findings published 7 years later, the 2019 event takes on a deeper resonance. The light echoes showed that Sagittarius A star had erupted at 10,000 times its current brightness within the past millennium. The 2019 brightening showed that even today, even during what we classify as a quiet epoch, the black hole can surge to 75 times its baseline without warning. These are not contradictory observations. They are points on a continuum, a spectrum of variability that ranges from routine small flares through anomalous modern brightenings, all the way to ancient eruptions powerful enough to illuminate molecular clouds for centuries. The Galactic Center's central engine does not have an off switch. It has a throttle, and the throttle moves. This finding connects to the broader picture of what has been discovered in the immediate environment of the black hole over the preceding 2 decades. The Event Horizon Telescope showed the accretion flow as it exists now. XRISM showed that the accretion flow was recently, by cosmic standards, far more violent. And the stars orbiting in this environment have been revealing just how extreme the gravitational conditions are for anything that ventures close. The star Stu was the first to demonstrate this in unforgettable terms. Stu has a mass roughly 14 times that of the Sun, making it a hot, luminous blue giant. Its orbit around Sagittarius A star takes approximately 16 years, and it follows a highly elongated elliptical path. At its closest approach, called periaps, Stu passes within roughly 120 astronomical units of the black hole, approximately 3 times the distance from the Sun to Pluto. At that point, it reaches a velocity of approximately 7,650 kilometers per second, roughly 2.5% of the speed of light. This is not some exotic neutron star or a wisp of infalling gas. This is a full-size star, many times more massive than the Sun, being whipped around a supermassive black hole at relativistic speeds. Stu's orbit became a laboratory for testing fundamental physics in ways that no terrestrial experiment can replicate. The first major result came in 2018, during Stu's closest approach to Sagittarius A star. As the star plunged deep into the black hole's gravitational well, the gravity instrument at the Very Large Telescope and the team led by Reinhard Genzel measured a phenomenon called gravitational redshift. General relativity predicts that light climbing out of a strong gravitational field loses energy, shifting toward longer, redder wavelengths. The deeper the gravitational well, the greater the shift. As Stu swung through periaps at thousands of kilometers per second, the light from the star was measurably redshifted beyond what its velocity alone would produce. The excess redshift matched the predictions of general relativity with extraordinary precision. It was the first clear detection of gravitational redshift from A star orbiting a supermassive black hole, confirming that space-time itself was being deformed around the star's trajectory in exactly the way Einstein's equations demanded. 2 years later, in 2020, the same team detected an even subtler effect, the Schwarzschild precession of Stu's orbit. In Newtonian gravity, a single object orbiting a central mass traces a fixed ellipse that repeats identically with every revolution. General relativity predicts a deviation. The curvature of spacetime near a massive object causes the elliptical orbit to rotate slowly, so that the point of closest approach shifts slightly with each revolution. The orbit does not close on itself. It traces a rosette pattern, like the petals of a slowly blooming flower. The gravity instrument measured this precession for Stu's orbit around Sagittarius A star, and the result matched Einstein's prediction to within the measurement uncertainty. It was the first time Schwarzschild precession had been observed around a supermassive black hole. A theory formulated in 1915, using pen and paper in a world without radio telescopes or infrared detectors, had predicted the exact behavior of A star orbiting a 4 million solar mass black hole over a century before the technology existed to observe it. The fabric of spacetime near Sagittarius A star was warped in exactly the way general relativity demanded. But Stu was not the closest star to the black hole, not even close. In 2022, a team led by Florian Peisker at the University of Cologne announced the discovery of I star designated S4716. Using data from 5 different instruments spanning 2 decades of observations and employing sophisticated image filtering techniques to see past the overwhelming glare of Stu, the team confirmed that S4716 orbits Sagittarius A star in just 4 years. 4 years. It completes a full revolution around a supermassive black hole in less time than it takes many graduate students to finish a doctoral degree. At its closest approach, S4716 comes within approximately 100 astronomical units of the black hole. At that distance, it reaches speeds of roughly 8,000 kilometers per second, more than 2.5% of the speed of light. The existence of S4716 was bewildering for multiple reasons. First, it meant that stable stellar orbits were possible even closer to the black hole than Stu's orbit, in a region where tidal forces are immense and the gravitational environment is extraordinarily hostile. Second, the star could not have formed at that location. Stars form from collapsing molecular clouds, and molecular clouds cannot survive the tidal shear that close to a 4 million solar mass black hole. S4716 had to have migrated inward from a greater distance, likely through gravitational interactions with other stars and objects in the crowded central cluster. Its current orbit represents the endpoint of a chaotic dynamical process that flung it inward and trapped it in a tight, fast loop around one of the most extreme objects in the galaxy. And even S4716 is not the record holder for closest approach. Another star in the same cluster, S4714, follows a 12-year orbit with an extreme eccentricity of approximately 0.985. This means its orbit is almost a straight line, plunging inward toward the black hole and then swinging back out to a much greater distance. At periaps, S4714 passes within an estimated 12.6 astronomical units of Sagittarius A star, though the measurement uncertainty on this figure remains large. If the estimate holds, that is barely farther than the distance from the Sun to Saturn. At that range, the star screams past the black hole at approximately 8% of the speed of light, 24,000 kilometers every second. A full-size star, moving at a velocity that makes the fastest human spacecraft look stationary by comparison, in a gravitational field so warped that space-time itself is being noticeably deformed around the orbiting object. These stars are not anomalies. They are members of a growing catalogue of S-cluster objects that have been identified, tracked, and characterized through years of painstaking infrared observation. Each new detection pushes the boundary of what astronomers thought was possible in the vicinity of a supermassive black hole. Each new orbit reveals more about the gravitational landscape of the galactic center, and collectively, they paint a picture of an environment where matter does not merely exist near the black hole. It races, plunges, and survives in conditions that no textbook written in the 20th century could have anticipated. The combination of these findings, the EHT shadow image, the polarized magnetic field maps, the XRISM light echoes, the star orbits, creates a layered and progressively more disturbing portrait of the galactic center. At the base of it all sits the black hole, 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun, bending space-time so severely that light itself curves around it in a bright ring visible from across the galaxy. Immediately surrounding it, a turbulent accretion flow of magnetized plasma spirals inward, heated to billions of degrees, flaring unpredictably and threaded with magnetic fields organized enough to suggest the potential for jet formation. Reflected in the molecular clouds around the center, a record of past outbursts 10,000 times brighter than anything we have observed directly, echoing through the region like the aftershock of an explosion that has only recently subsided, and weaving through all of it, individual stars on orbits so fast and so tight that they would have been dismissed as physically impossible just 30 years ago. None of these findings exist in isolation. Each one connects to the others, reinforcing the same central revelation. The center of the Milky Way is not a quiet gravitational anchor around which the galaxy gently rotates. It is an active, dynamic, violent environment that has been undergoing extreme physical processes for millennia and shows every sign of continuing to do so. The quiet phase we observe today may be just that, a phase, a brief pause in a history of energetic outbursts that recur on timescales short enough to overlap with human civilization. This is what makes the discoveries hard to accept. Not any single finding by itself, but the cumulative weight of evidence revealing that the center of the galaxy you see from your backyard on a summer night contains an environment where stars move at percentages of light speed, where magnetic fields spiral at the boundary of a space-time abyss, where gas flares to temperatures that dwarf the cores of the most massive stars, and where echoes of explosions, thousands of times more powerful than anything currently visible, are still ringing through surrounding clouds of molecular gas. The peaceful Milky Way above us is a surface. Beneath that surface, at the gravitational bottom of the galaxy, physics operates in a regime so far removed from everyday experience that the language we use to describe ordinary space barely applies. And we are not looking at a distant abstraction, we are looking at the core of our own home. But the environment near Sagittarius A star is even stranger than these observations alone suggest, because the stars orbiting the black hole are not the only objects inhabiting this extreme region. Theoretical models and indirect observational evidence point to something far more unsettling lurking in the central parsec, an invisible population of dead stars concentrated around the supermassive black hole, interacting with the living stars in ways that are only now beginning to be understood. The galactic center is not merely extreme, it may be actively grinding its own stellar population into oblivion. The space you know is gentle. That is not a poetic observation. It is a measurable physical fact. In the solar neighborhood, gravity is a background whisper. The sun holds its planets in stable orbits that have not changed meaningfully in billions of years. Stars drift past each other at relative velocities of a few tens of kilometers per second. The interstellar medium, the thin gas between stars, has a density of roughly 1 atom per cubic centimeter, a vacuum so perfect that no laboratory on Earth can replicate it. Temperatures in this medium range from a few thousand degrees in warm ionized regions to just a few degrees above absolute zero in dense molecular clouds. Nothing explodes, nothing tears, nothing moves fast enough to distort the passage of time. This is the space that shaped human intuition. This is the space we imagine when someone says the word universe. Now erase all of that. Every assumption, every intuition, every comfortable sense of how matter and energy behave in the cosmos. Because the inner parsec of the Milky Way, the volume of space within roughly 3 light-years of Sagittarius I star, operates under a completely different regime of physics. Not different laws. The same laws of nature apply everywhere, but the conditions are so far outside the range of anything in the solar neighborhood that the familiar consequences of those laws become unrecognizable. Gravity is not a whisper at the galactic center. It is a scream, and everything that exists within earshot of that scream is being shaped, stressed, heated, accelerated, and in many cases destroyed by forces that most of the galaxy never encounters. Start with tidal forces, because they are the most viscerally understandable way the galactic center differs from ordinary space. Tidal force is the difference in gravitational pull between the near side and far side of an object. The moon raises tides on Earth because the side of our planet facing the moon feels a slightly stronger gravitational tug than the side facing away. The difference is small, enough to move ocean water by a meter or two, but not enough to threaten the structural integrity of the planet. Near Sagittarius A star, tidal forces are not small. They are catastrophic. The gravitational field of a 4 million solar mass black hole changes with distance, according to an inverse cube relationship. This means that as you move closer, the gradient of gravity steepens with savage rapidity. At the distances where S-cluster stars orbit, the tidal force across an object the size of a typical star is already enormous. A star passing within a few dozen astronomical units of the event horizon experiences a difference in gravitational pull between its near hemisphere and far hemisphere that can exceed the star's own self-gravity, the internal force holding it together. When that threshold is crossed, the star does not merely feel stretched. It comes apart. The near side accelerates toward the black hole faster than the far side can follow, and the star elongates into a thin stream of superheated plasma spiraling inward. This process is called a tidal disruption event, and it is one of the most violent individual phenomena in astrophysics. Tidal disruption events around supermassive black holes in distant galaxies have been observed dozens of times by X-ray and optical telescopes. They produce luminous flares that can briefly outshine the entire host galaxy, as the disrupted stellar material forms a rapidly accreting disk around the black hole and radiates furiously before disappearing beyond the event horizon. At Sagittarius A star, the conditions for tidal disruption exist permanently. Any star that wanders too close on an unfavorable orbit faces destruction. The tidal radius, the distance within which a sun-like star would be torn apart, sits at roughly 100 million kilometers from Sagittarius A star, depending on the star's density and internal structure. Compact stars like white dwarfs can survive closer approaches because their self-gravity is higher relative to their size. Diffuse giant stars are vulnerable at much greater distances because their loosely bound outer layers are easy prey for the tidal gradient. The S-cluster stars currently survive because their orbits, while extreme, do not bring them within the tidal disruption radius. 4714, with its closest approach of roughly 12 astronomical units, passes dangerously near but remains intact because it is a relatively compact main sequence star. A red giant of the same mass would not survive the same orbit. Its distended outer envelope would be stripped away, feeding a transient burst of accretion onto the black hole. This is not hypothetical. Astronomers have identified objects near Sagittarius A star that appear to be tidally interacting with the black hole, and the most dramatic case played out in something close to real time. The objects known as GON and G2 are compact infrared sources on orbits that bring them close to Sagittarius A star. G2, first identified in 2011 by a team using the Very Large Telescope, attracted worldwide attention because its orbital trajectory would carry it to within roughly 150 astronomical units of the supermassive black hole in 2014. For 3 years leading up to the close approach, observatories on multiple continents trained their instruments on the object, watching it fall deeper into the black hole's gravitational well. The anticipation was enormous. If G2 was a simple gas cloud, as initial observations suggested, the tidal forces at periaps should tear it apart spectacularly. The disrupted material would spiral onto the black hole, potentially triggering a dramatic increase in accretion rate and producing observable flares across multiple wavelengths. Some researchers predicted that the event could briefly increase Sagittarius A star's luminosity by orders of magnitude. For the first time, astronomers believed they might witness a feeding event at a supermassive black hole in real time, not in a distant galaxy, but in their own. What actually happened was more complex and, in its own way, more revealing. As G2 approached periaps, infrared observations showed the object elongating. Tidal forces were clearly stretching it along its orbital path, pulling the leading edge ahead and dragging the trailing edge behind. The stretching was visible in spectroscopic data, which showed the emission from G2 broadening in velocity space as the front and back of the object accelerated at different rates. The tidal gradient was doing exactly what physics predicted, but G2 did not disintegrate. It passed through periaps and emerged on the other side, battered, elongated, but fundamentally intact. The anticipated fireworks, the surge in accretion, the burst of radiation never materialized at the scale many had expected. The survival of G2 told scientists something important. The object could not be a simple gas cloud. An unsupported cloud of gas at that mass and density would have been shredded beyond recovery. G2 had to contain something holding it together, some internal source of gravity or pressure that resisted the tidal gradient. The leading interpretation shifted. G2 might be a young star embedded in a thick envelope of gas and dust, or the product of a recent binary star merger, still shrouded in the debris of the collision. In either case, a central dense object was providing the gravitational cohesion needed to survive the encounter. But the distortion was real. The stretching was measured and quantified. G2's encounter with Sagittarius A star remains one of the most detailed observations of tidal interaction with a supermassive black hole ever conducted, and it confirmed that the forces at work in the galactic center are not abstractions. They are strong enough to visibly reshape objects on timescales of months and years, observable from 26,000 light-years away through the intervening dust and gas. GON, a similar object on a different orbit, had passed close to Sagittarius A star earlier, around 2001, and showed comparable properties: a compact infrared source, with characteristics suggesting a dust-enshrouded stellar object, rather than a bare gas cloud. Some researchers have proposed that GON, G2, and possibly additional objects in the galactic center represent a population of binary star merger remnants, created when the intense gravitational environment of the inner parsec forces binary systems into collisions. If true, the galactic center is not just destroying stars through tidal disruption, it is also forcing stars to collide and merge, producing entirely new classes of objects that do not exist in the calmer parts of the galaxy. Move closer to the black hole and the tidal environment becomes even more punishing. But something else begins to dominate: the accretion flow itself. Sagittarius A star is surrounded by a structure of hot, magnetized gas that is spiraling slowly inward under the combined influence of gravity and angular momentum. This gas is not dense by terrestrial standards, but it is extraordinarily hot. Temperatures in the innermost regions of the accretion flow reach tens of billions of degrees, far exceeding the core temperature of any star. At these temperatures, matter exists as fully ionized plasma, a seething soup of protons, electrons, and heavier nuclei stripped of their electrons, all moving at velocities approaching the speed of light. This plasma does not orbit the black hole in neat circular paths. The accretion flow around Sagittarius I star is classified as a radiatively inefficient accretion flow, sometimes called an advection-dominated accretion flow. In this regime, the gas is so hot and so sparse that it cannot radiate energy efficiently. Instead of cooling and settling into a thin disk like the accretion structures around more active black holes, the gas around Sagittarius A star puffs up into a thick, turbulent, quasi-spherical structure. Energy generated by gravitational compression is trapped within the flow and carried inward along with the gas rather than being radiated away. This is part of why Sagittarius A star appears so dim compared to its theoretical maximum luminosity. The accretion flow is not efficiently converting gravitational energy into light. It is swallowing that energy whole, carrying it across the event horizon into permanent informational oblivion. But inefficient does not mean inactive. The plasma in the accretion flow is threaded with magnetic fields, and those fields are turbulent, tangled, and prone to violent reconfiguration. Magnetic reconnection events, in which stressed field lines snap and reconnect in lower energy configurations, release enormous bursts of energy into the surrounding plasma. These events are the most widely accepted explanation for the X-ray and infrared flares that astronomers observe from Sagittarius A star on a near-daily basis. Each flare represents a localized magnetic explosion in the accretion flow, accelerating electrons to relativistic speeds and producing synchrotron radiation detectable across multiple wavelengths. The timescale of these flares is itself revealing. Gas at the innermost stable circular orbit of a non-spinning black hole of 4 million solar masses completes one full revolution in approximately 30 minutes. This means the accretion environment reshapes itself on timescales comparable to a lunch break. Structures form, flare, and dissipate in the time it takes to watch a television episode. The environment near Sagittarius A star is not just extreme in magnitude, it is extreme in tempo. Everything happens fast, violently, and repeatedly, on cycles too short for any structure to persist for long. But tidal forces and accretion physics are not the only sources of hostility in the central parsec. There is a third axis of extremity that receives less attention, but is no less significant: the radiation environment itself. The inner parsec of the Milky Way is bathed in radiation at intensities that dwarf anything found in the solar neighborhood. The sources are multiple and overlapping. Dozens of massive luminous stars within the central cluster pour ultraviolet radiation into the surrounding space at rates millions of times greater than the Sun's total output. These stars drive powerful stellar winds, outflows of charged particles moving at thousands of kilometers per second. Where winds from neighboring stars collide, the kinetic energy of the collision is converted into thermal energy, heating the gas to tens of millions of degrees and producing diffuse X-ray emission that permeates the entire central region. The cumulative effect of these colliding winds creates a persistent hot plasma that fills the spaces between stars, a bath of superheated gas that would sterilize any planetary surface exposed to it. Layered on top of the stellar radiation is the output from the accretion flow around Sagittarius A star itself. Even in its current quiet state, the black hole produces X-ray and radio emission that illuminates the surrounding environment. During flares, the X-ray luminosity spikes by orders of magnitude, sending pulses of ionizing radiation outward through the central parsec. And underlying all of this is an elevated density of cosmic rays, high-energy particles accelerated by supernova remnants, stellar wind shocks, and possibly by processes associated with the accretion flow itself. Cosmic ray densities in the galactic center exceed those in the solar neighborhood by factors estimated between 10 and 100, depending on energy range. These particles penetrate deep into molecular clouds, ionizing gas that would otherwise remain shielded from external radiation, and they contribute to the overall energy budget of the region in ways that are still being quantified. The combined radiation field of the central parsec creates an environment where the very concept of a stable planetary surface becomes questionable. Ultraviolet flux from nearby massive stars would strip atmospheres from exposed planets. X-ray flares from Sagittarius A star would periodically dose any nearby world with ionizing radiation at levels incompatible with complex surface biology. Cosmic ray bombardment would drive chemical reactions in planetary atmospheres that could destroy protective ozone layers and alter surface conditions beyond habitability. None of this means planets cannot exist in the galactic center. It means that planets there face an unrelenting assault from every part of the electromagnetic spectrum, delivered by sources that are collectively more luminous, more energetic, and more numerous than anything in the quiet suburbs where our solar system orbits. The organized magnetic fields revealed by the Event Horizon Telescope's polarization analysis carry an additional implication when viewed alongside this accretion physics. The coherence of those spiraling field lines is not merely visually striking. It is a prerequisite for a specific theoretical configuration called the magnetically arrested disk state, in which magnetic fields become strong enough to temporarily impede the infall of gas, building up pressure until the magnetic barrier breaks and a surge of material plunges inward. Magnetically arrested disks are associated with the most powerful jet-producing black holes in the universe. If Sagittarius I star operates in or near this state, the implication extends beyond the jet possibility raised by the M87 comparison. It means the accretion flow itself is in a regime where magnetic forces periodically dam and release infalling material, creating a cycle of build-up and collapse that could drive the episodic outbursts recorded in the XRISM light echoes. This brings us to the inhabitants of this infernal region that no telescope has directly seen, but that physics insists must be there: the stellar mass black holes. When a massive star exhausts its nuclear fuel and its core collapses beyond the threshold of neutron degeneracy pressure, the result is a stellar mass black hole, typically ranging from about 5 to several tens of solar masses. These objects are the corpses of the galaxy's most massive stars, and theoretical models predict that the Milky Way contains roughly 100 million of them scattered throughout its volume. Most drift through the galaxy in obscurity, invisible unless they happen to accrete matter from a nearby companion star. But the galactic center is not like the rest of the galaxy. It is a gravitational sink, the lowest point in the Milky Way's gravitational potential. And over billions of years, a process called dynamical friction has been dragging heavy objects inward. Dynamical friction works through gravitational interactions between a massive object and the surrounding field of lighter objects, predominantly stars. As a stellar mass black hole moves through a dense stellar environment, it gravitationally attracts nearby stars, creating a slight overdensity behind it. This trailing wake of stars exerts a gravitational pull backward on the black hole, slowing it down. Slower speed means a tighter orbit. Over millions and billions of years, this braking effect causes heavy objects to spiral inward toward the galactic center, accumulating in the innermost regions. Lighter stars experience less dynamical friction and remain at larger radii. The result is mass segregation. The heaviest objects sink to the center. In 2000, astrophysicists Jordi Moralda-Escudé and Andrew Gould at Ohio State University calculated that this process should have deposited approximately 25,000 stellar mass black holes into the central parsec of the back Milky Way, 25,000 invisible gravitational engines, each several to tens of times the mass of the Sun, crowded into a volume just 3 light-years across, orbiting the supermassive black hole in a dark, unseen swarm. This is not speculation based on loose assumptions. It is a quantitative prediction grounded in well-understood gravitational dynamics, stellar evolution models, and the known properties of the galactic bulge's stellar population. For 18 years, this prediction remained purely theoretical. No observational evidence could confirm or deny the presence of thousands of stellar mass black holes packed into the galactic center. Then, in 2018, a team led by Chuck Haley at Columbia University published results from a deep analysis of archival data from NASA's Chandra X-ray Observatory. Chandra had been observing the galactic center repeatedly for years, building up a cumulative dataset of X-ray sources in the region. Haley's team sifted through this data looking for a specific signature: faint, hard X-ray sources consistent with quiescent X-ray binaries, systems in which a stellar mass black hole is accreting at a low rate from a companion star and producing a characteristic X-ray spectrum. They found 12 candidates within roughly 3 light-years of Sagittarius A star, 12 faint X-ray sources whose spectra, luminosities, and spatial distribution match the expected properties of black hole X-ray binaries in a quiescent state. 12 does not sound like 25,000, but the team's analysis explained the discrepancy. X-ray binaries are only a tiny fraction of the total black hole population, because most stellar mass black holes are isolated, drifting alone without a companion to provide accretable material. For every black hole that happens to be in a binary system and producing detectable X-rays, hundreds or thousands of isolated black holes orbit invisibly in the same volume. The 12 detected sources, extrapolated through well-calibrated models of binary fraction and X-ray luminosity function, implied an underlying population of between 10,000 and 40,000 stellar mass black holes in the central parsec. The prediction made in 2000 had been observationally confirmed to within its expected range. This invisible swarm of stellar mass black holes transforms the galactic center from an extreme environment into something closer to a gravitational minefield. Every object orbiting near Sagittarius I star is simultaneously navigating the tidal field of the supermassive black hole and the gravitational perturbations of thousands of unseen compact remnants. Close encounters between stars and stellar mass black holes can fling stars onto radically different orbits, accelerate them to extreme velocities, or strip material from their outer layers. The dynamics are not those of a clean two-body gravitational problem like a planet orbiting a star. They are the chaotic, multi-body dynamics of a crowded gravitational arena where the players range from stellar mass black holes to neutron stars to main sequence giants, all threading through the crushing tidal field of a central mass 4 million times the Sun. In March of 2025, a team of researchers, including members from the University of Cologne and the Helmholtz Institute, published a study in Astronomy and Astrophysics that pushed this picture to a disturbing new conclusion. The paper, which examined the collision rates between stellar mass black holes and ordinary stars in the innermost regions of the galactic center, found that direct physical collisions between these objects could deplete the most massive stars within the S-cluster, on timescales of just a few million years. The mechanism is straightforward in principle, though violent in execution. A stellar mass black hole on a plunging orbit passes so close to an ordinary star that the two objects physically intersect. The black hole, being far denser and more gravitationally potent, tears through the star or disrupts it entirely, scattering stellar material into the surrounding environment. The researchers termed this process the star grinder, and they demonstrated that the collision rates implied by the estimated black hole cluster density were sufficient to explain one of the long-standing puzzles of the galactic center, the absence of the most massive O-type stars from the S-cluster. O-type stars are the heaviest and most luminous main sequence stars, with masses exceeding roughly 15 to 20 times that of the Sun. If the S-cluster formed through a standard star formation process, it should contain a population of these massive stars. It does not. The most massive S-cluster members are B-type stars, one category below O-type in the stellar classification system. The star grinder mechanism offers a natural explanation. O-type stars, being the largest physical targets, are destroyed preferentially by collisions with the unseen black hole population. They are ground down faster than they can be replenished, leaving behind only the smaller, more compact B-type stars that present smaller collision cross-sections. This finding also connected to another puzzle, the apparent deficit of hypervelocity star counterparts in the galactic center. Hypervelocity stars are objects ejected from the galactic center at speeds exceeding the escape velocity of the Milky Way. They are thought to be produced when binary star systems interact with Sagittarius A star, with one star being captured and the other flung outward at tremendous speed. If such ejections occur regularly, there should be a corresponding population of stars left behind on tightly bound orbits near the black hole. The observed deficit of these counterpart stars in the S-cluster can be explained if the star grinder mechanism is destroying them after they are captured, before they can be observed as a stable population. But the stellar mass black holes in the central parsec are not merely grinding down the stars around them, they are also, slowly and inexorably, spiraling towards Sagittarius A star itself. The same dynamical friction that dragged them inward from the broader galaxy continues to operate within the central cluster, and for the black holes that reach the innermost orbits, a second and even more fundamental process takes over: gravitational wave emission. When a stellar mass black hole orbits close enough to a supermassive black hole, general relativity predicts that the orbital motion generates ripples in the fabric of space-time itself. These gravitational waves carry energy away from the system. As energy is lost, the orbit shrinks. The stellar mass black hole spirals gradually closer, completing thousands or millions of orbits in a slow, tightening descent toward the event horizon. Each orbit brings it fractionally nearer. Each revolution radiates a little more energy into the gravitational wave background. The process is called an extreme mass ratio in spiral, abbreviated EMRI, and it represents one of the most information-rich gravitational wave sources that physicists have ever conceived. The reason EMRIs are so scientifically valuable is that the smaller object traces out the space-time geometry of the larger one with extraordinary precision. As the stellar mass black hole spirals inward, its gravitational wave signal encodes a detailed map of the curvature of space-time near the supermassive black hole's event horizon. The waveform carries information about the mass, the spin, and the quadrupole moment of Sagittarius A star, parameters that can be compared against the predictions of general relativity with a precision that no electromagnetic observation can match. If spacetime near a supermassive black hole deviates from Einstein's predictions in any measurable way, an EMRI waveform would reveal it. These signals cannot be detected by ground-based gravitational wave observatories like LIGO or Virgo. The frequencies are too low, falling in the millihertz range, far below the sensitivity band of terrestrial detectors. Detecting them requires a space-based observatory, and one is being built. The Laser Interferometer Space Antenna, known as LISA, is a joint mission of the European Space Agency and NASA currently planned for launch in the mid-2030s. LISA will consist of 3 spacecraft flying in formation, separated by 2.5 million kilometers, forming a triangular gravitational wave detector in solar orbit. Its primary science targets include merging supermassive black holes, compact binary systems throughout the galaxy, and extreme mass ratio in spirals from galactic centers. The Milky Way's own central parsec, with its estimated population of tens of thousands of stellar mass black holes concentrated around a 4 million solar mass supermassive black hole, is one of the most promising environments in the observable universe for producing detectable EMRIs. The sheer number of compact remnants increases the probability that at any given time, at least one stellar mass black hole is in the late stages of an inspiral, emitting gravitational waves at frequencies and amplitudes within LISA's reach. If LISA detects an EMRI signal originating from the direction of Sagittarius A star, it would provide a direct probe of space-time geometry at the event horizon of our own galaxy's central black hole, a measurement that no telescope operating in any wavelength of light could ever achieve. This possibility connects the invisible black hole swarm to a future detection channel that is fundamentally different from anything discussed so far in this story. Every observation described up to this point, the EHT image, the XRISM echoes, the star orbits, the Chandra X-ray binaries, relies on electromagnetic radiation, on photons. Gravitational waves are not photons. They are distortions in the fabric of spacetime itself, propagating outward at the speed of light but carrying information through an entirely separate physical channel. The galactic center has been broadcasting in this channel for billions of years, as stellar mass black holes have spiraled inward, merged, and been swallowed by Sagittarius A star. We have simply never had the ability to listen. LISA will change that, and when it does, the galactic center will reveal yet another layer of its violence, one written not in light but in the trembling of space itself. The implications ripple outward from the galactic center. If the inner parsec of the Milky Way contains a dense cluster of stellar mass black holes actively grinding through the surrounding stellar population, then the galactic center is not merely a place where extreme things happen passively, as consequences of proximity to a supermassive black hole. It is a place where destruction is an ongoing, multi-agent process, driven by an invisible infrastructure of dead stars that pervades the region like an unseen web of gravitational hazards. Stars do not simply orbit Sagittarius A star and survive by staying outside the tidal disruption radius. They must also survive a gauntlet of encounters with compact remnants that can destroy them through direct collision, gravitational scattering, or tidal stripping at close approach. And then there is the problem that started this entire line of inquiry decades ago and still refuses to yield a clean solution: the paradox of youth. The S-cluster stars are young. Their spectral types, luminosities, and temperatures indicate ages of only a few million to a few tens of millions of years. In the broader galaxy, stars of these types are found in regions of active star formation, embedded in molecular clouds or associated with stellar nurseries. Near Sagittarius A star, no such nursery should be able to exist. The tidal shear from the supermassive black hole disrupts molecular clouds before they can collapse into stars. The radiation environment is intense. The gravitational dynamics are chaotic. Every standard model of star formation says these stars should not be here. Several competing explanations have been proposed. One model suggests that the young stars formed in a massive, self-gravitating disk of gas that once orbited Sagittarius A star at a distance of a few tenths of a parsec. If such a disk were dense enough, its own gravity could overcome the tidal disruption from the black hole, allowing fragments to collapse into stars. This model can explain the observed disk-like distribution of some young stars in the galactic center, particularly the so-called clockwise disk of massive stars orbiting at roughly 1/10 of a parsec from the black hole. But it struggles to explain the S-cluster stars, which orbit on randomly oriented, highly eccentric paths that do not resemble the remnants of a disk population. Another model proposes that the S-cluster stars were originally members of binary systems or small stellar groups that formed at greater distances and migrated inward through dynamical interactions. As a binary approaches the supermassive black hole, tidal forces can disrupt the pair, capturing one star on a tight orbit and ejecting the other at high velocity. This mechanism, called the Hills process, after the physicist Jack Hills, who first described it in 1988, can populate the inner region with young stars without requiring local star formation. It also naturally produces hypervelocity stars as the ejected partners, which have indeed been observed fleeing the galaxy at speeds exceeding 1,000 kilometers per second. The Hills process is currently the most widely favored explanation for the S-cluster, but it raises its own questions. The process requires a steady supply of binary systems falling toward the galactic center on nearly radial orbits. The rate at which binaries need to be delivered to produce the observed S-cluster population is high enough that some researchers find it uncomfortable. The supply chain must have been operating continuously for millions of years, delivering victims to the black hole's gravitational jaws at a pace that implies a large reservoir of infalling material in the broader galactic center region. Taken together, these phenomena transform the inner parsec of the Milky Way into something that has no real analogue in human experience or in the broader galactic disk. It is a region where the supermassive black hole defines the gravitational landscape so completely that every other force becomes secondary, where tidal gradients can shred stars that wander too close, where an accretion flow of billion-degree plasma flares and churns on timescales of minutes, where organized magnetic fields spiral at the edge of the event horizon with a structure that hints at dormant jet launching capability, where the radiation environment from massive stellar winds, X-ray flares, and elevated cosmic ray densities bathes every surface in ionizing energy, where an invisible population of tens of thousands of stellar mass black holes grinds through the surrounding stars like millstones, where stars that should not exist orbit at percentages of light speed on paths that were considered physically impossible within living memory, where the light from ancient explosions 10,000 times brighter than anything currently observed is still echoing off the walls of the surrounding molecular clouds. This is not a theoretical model of an extreme environment. Every element of this picture is grounded in direct observation, peer-reviewed analysis, or well-constrained theoretical prediction based on confirmed physical principles. The star orbits are tracked in real time. The EHT image has been published and independently verified. The XRISM light echoes have been spectrally resolved to laboratory-grade precision. The Chandra X-ray binary detections have been published and subjected to independent statistical analysis. The stellar mass black hole population follows from gravitational dynamics that have been tested in countless other astrophysical contexts. The star grinder collision rates are derived from observed stellar densities and well-understood interaction cross-sections. The radiation environment has been measured across radio, infrared, X-ray, and gamma-ray wavelengths by multiple independent observatories. The galactic center is not a mystery in the sense that scientists do not know what is happening there. They know. What makes it hard to accept is the sheer accumulation of extremes packed into a single region of our own galaxy. Each individual finding is remarkable on its own. Stars orbiting at 8,000 kilometers per second would be headline science anywhere in the universe. A supermassive black hole shadow image would define any observatory's legacy. X-ray echoes revealing 10,000-fold brightness increases would rewrite the history of any galactic nucleus. A predicted population of 25,000 invisible black holes grinding down the stellar population would transform any theoretical framework. But at the center of the Milky Way, all of these things happen in the same place, at the same time, within a volume of space so small that light crosses it in a few years, and they happen not in some distant alien galaxy at the edge of the observable universe, but at the gravitational center of the galaxy, whose stars you can see from your own backyard. That proximity is what makes the findings so difficult to reconcile with the human experience of the Milky Way as a calm, familiar presence in the night sky. The galactic center does not merely contain extreme objects, it is an extreme environment, a self-reinforcing system in which gravity, magnetism, radiation, and orbital mechanics conspire to create conditions found nowhere else within 26,000 light-years of Earth. And the most unsettling aspect of this environment is not what it does to matter and light. It is what it reveals about the galaxy we thought we knew. There is a moment that every astronomer who studies the galactic center eventually describes, though they use different words for it. It happens not in the observatory and not at the telescope. It happens afterward, sometimes days or weeks later, when they step outside on a clear night and look up. The Milky Way is there, the same band of light they have seen since childhood, draped across the sky in its familiar arc. And for the first time, it looks wrong. Not visually wrong, emotionally wrong. Because they now know what is hiding at its center, and the knowledge creates a dissonance that never fully resolves. The galaxy still looks peaceful. The galaxy still looks safe. But they know it is neither of those things, and the gap between what they see and what they know becomes a permanent feature of how they experience the night sky. That dissonance is not a failure of imagination. It is a collision between two fundamentally incompatible scales of understanding. Human perception evolved to process the immediate environment. Distances you can walk, temperatures you can feel, speeds you can outrun, dangers you can see approaching. The Milky Way, as it appears to the naked eye, fits comfortably within this perceptual framework. It is beautiful. It is distant. It is still. Nothing about its appearance triggers alarm, because nothing about its appearance communicates the physical reality of what is happening. 26,000 light-years away at its gravitational core, the band of light you see overhead is a projection, a two-dimensional compression of a three-dimensional structure that stretches 100,000 light-years across and contains more violence at its center than most people encounter in an entire education about the cosmos. This is the deepest reason why what scientists found near Sagittarius A star is hard to accept. It is not that any single finding strains credulity. Each discovery, taken individually, follows logically from the physics of supermassive black holes, extreme gravity, and high-energy astrophysics. Stars orbit fast near massive objects. Gas heats up in accretion flows. Magnetic fields reconnect and produce flares. Compact remnants accumulate through dynamical friction. None of this violates known physics. None of it requires exotic or speculative mechanisms. The difficulty is not intellectual. It is emotional. It is the difficulty of reconciling the galaxy you experience, the one that hangs silently in the sky like a painting, with the galaxy that actually exists, the one whose center is a furnace of gravitational violence, operating on timescales and energy scales that dwarf anything in the human sensory repertoire. Consider what the XRISM findings from 2026 actually mean when you translate them out of the measured language of astrophysical papers and into plain terms. Within the past few hundred to 1,000 years, possibly during the era of the Crusades or the European Renaissance or the Ming Dynasty, Sagittarius A star underwent an eruption so intense that it briefly shone 10,000 times brighter in X-rays than its current output. That eruption sent a pulse of high-energy radiation outward through the galactic center, illuminating molecular clouds like a flashbulb firing in a dark room. The light from that eruption, reflected and delayed by clouds at varying distances, is still arriving at Earth today, carrying spectral fingerprints that the XRISM telescope can read with laboratory precision. The black hole at the center of our galaxy threw a tantrum within recorded human history, and we are only now learning about it because the evidence has been bouncing around the galactic center for centuries, waiting for an instrument sensitive enough to decode it. This finding demolishes the comfortable narrative that Sagittarius A star is a sleeping giant. It is not sleeping, it is resting between episodes. The distinction matters enormously. A sleeping giant implies permanence, a state that will persist indefinitely. A resting giant implies cyclicity, a pattern of eruption and quiescence that repeats on timescales that may be short by cosmic standards. If the most recent major outburst occurred within the past millennium, then similar outbursts likely occurred in preceding millennia, and similar outbursts will likely occur in future millennia. The quiet Sagittarius A star we observe today is a snapshot, not a portrait. It captures one moment in a longer story of recurrent violence. The 2024 polarization results from the Event Horizon Telescope reinforce this interpretation in a way that is subtly more unsettling. The discovery that Sagittarius A star's magnetic field structure closely resembles that of M87's black hole carries an implication that extends well beyond the technical details of magnetic field geometry. M87's black hole produces a relativistic jet, a collimated beam of plasma accelerated to near light speed that extends 5,000 light-years into the intergalactic medium. That carries enough energy to inflate vast bubbles of hot gas in the surrounding galaxy cluster. It is one of the most energetic sustained phenomena in the observable universe. The magnetic field configuration required to launch and sustain such a jet is specific and well studied, and that same configuration, or something strikingly similar to it, has now been found at the event horizon of the black hole at the center of our galaxy. No jet has been confirmed emerging from Sagittarius A star, but the magnetic architecture that produces jets in other systems appears to be in place. Several scenarios follow from this observation, and none of them are comforting. The first possibility is that Sagittarius I star currently produces a faint jet that existing telescopes cannot detect. Some radio observations have identified elongated structures near the galactic center that could be consistent with a weak or intermittent jet, but the evidence is not conclusive. The second possibility is that Sagittarius I star produced a jet in the past, during one of its more active episodes, and the jet has since faded as the accretion rate declined. The third possibility is that the magnetic conditions for jet formation exist, but the accretion flow is currently too sparse to provide the energy needed to power one. In all three cases, the takeaway is the same. The central engine of the Milky Way possesses the infrastructure for a level of energy output that we associate with the most powerful active galactic nuclei in the universe. It is simply not exercising that capability at the present moment. This places Sagittarius A star in a broader context that further erodes the idea of the Milky Way as an ordinary, quiet galaxy. Across the observable universe, supermassive black holes occupy a spectrum of activity ranging from completely quiescent to spectacularly luminous. At one extreme, you have quasars, active galactic nuclei so bright that they can be detected across billions of light years, powered by supermassive black holes accreting matter at prodigious rates. At the other extreme, you have black holes like Sagittarius I star accreting at a tiny fraction of their maximum capacity and producing correspondingly modest luminosity. The standard assumption has long been that quiescent black holes are fundamentally different from active ones, that the Milky Way's central black hole occupies a settled, stable point on this spectrum. The XRISM and EHT findings challenge that assumption directly. Sagittarius A star is not settled. It is variable. It has been dramatically brighter in the recent past. It possesses the magnetic machinery associated with the most energetic black hole outflows known. The boundary between a quiet galactic nucleus and an active one may be less a wall and more a dial, and the evidence now suggests that our galaxy's dial has been turned up significantly within the last few thousand years. If Sagittarius A star were to undergo a major accretion event today, the practical consequences for life on Earth would be negligible. 26,000 light-years of distance, combined with the absorbing gas and dust between us and the galactic center, provides more than enough shielding against any radiation burst the black hole could realistically produce. The danger from the galactic center is not physical, it is conceptual. It is the realization that the galaxy you inhabit is not the stable, predictable structure it appears to be, but a system with a violently active core that flickers on and off over timescales that overlap with human civilization. Think about what this means for the broader population of galaxies in the universe. If the Milky Way's central black hole, one of the quietest known supermassive black holes, has recently demonstrated outbursts 10,000 times brighter than its current state, what does that say about the galactic centers we classify as dormant, based on even less observational data? The XRISM technique of reading light echoes from surrounding molecular clouds could in principle be applied to other nearby galaxies, mapping the recent activity history of their central black holes through reflected X-ray signatures. If similar patterns of episodic activity emerge, the fraction of galaxies with truly dormant central engines may be far smaller than current classifications suggest. The universe may contain far more intermittently active galactic nuclei than anyone has counted, galaxies that appear quiet in their current snapshot but carry evidence of recent violence in the molecular clouds surrounding their cores. The theoretical population of stellar mass black holes at the galactic center carries its own set of implications for how we understand the Milky Way's structure and evolution. If approximately 25,000 stellar mass black holes are concentrated within the central parsec, their collective mass amounts to roughly 100,000 to several hundred thousand solar masses, depending on the average mass per black hole. This is a small fraction of Sagittarius A star's 4 million solar masses, but it is not negligible. The gravitational influence of this swarm affects the orbits of nearby stars, contributes to the overall mass profile of the inner galaxy, and creates a dynamical environment whose complexity far exceeds what a single supermassive black hole in isolation would produce. The 2025 Star Grinder research illustrates how this complexity manifests in observable consequences. The depletion of massive O-type stars through collisions with stellar mass black holes is not merely an explanation for a missing stellar population. It is a demonstration that the galactic center is actively processing its own contents, converting luminous stars into disrupted remnants, feeding material into the surrounding environment, and reshaping the stellar demographics of the inner galaxy through a mechanism that operates continuously and invisibly. The galactic center is not a static collection of objects orbiting a central mass. It is a dynamic ecosystem in which gravitational interactions between visible and invisible components drive ongoing transformation of the stellar population. This ecosystem extends its influence beyond the immediate vicinity of Sagittarius A star. Hypervelocity stars ejected through the Hill's mechanism carry kinetic energy out of the galactic center and into the broader galaxy. Some of these stars reach escape velocity and leave the Milky Way entirely, becoming intergalactic wanderers. Others settle into the galactic halo on extreme orbits, carrying chemical signatures that trace their origin to the galactic center environment. These displaced stars serve as archaeological evidence of the processes occurring near Sagittarius A star, scattering clues across the galaxy like debris from an ongoing explosion. The chemical enrichment of the galactic center also tells a story of sustained violence. When massive stars die in supernova explosions, they scatter heavy elements into the surrounding interstellar medium. The galactic center, with its disproportionately high concentration of massive stars, has been a persistent source of heavy element production for billions of years. Gas in the central molecular zone, the ring of dense molecular material orbiting several hundred light-years from Sagittarius A star, shows elevated abundances of metals compared to gas in the outer galaxy. This enrichment reflects the accumulated output of countless stellar explosions in a region where the cycle of star formation, stellar death, and elemental recycling operates at an intensity unmatched elsewhere in the Milky Way. But the most profound implication of the galactic center findings is not about black holes, stars, or chemical abundances. It is about the nature of the galaxy itself. The Milky Way is not a uniform structure with a single character. It is a system with a gradient of extremity, smooth and gentle in its outer reaches, increasingly hostile and dynamic as you approach its gravitational core, and violently extreme in the innermost region surrounding the supermassive black hole. This gradient is not unique to our galaxy. Every major galaxy is believed to harbor a supermassive black hole at its center, and the physics that produces extreme conditions near Sagittarius A star operates identically near the central black holes of Andromeda, of Centaurus A, of M87, of every spiral and elliptical galaxy in the observable universe. The galactic center of the Milky Way is simply the nearest example of a universal phenomenon. The gravitational core of a galaxy is a profoundly different place from the peaceful suburbs where most stars, most planets, and presumably most life exists. This gradient of extremity has implications for the search for life beyond Earth. The habitable zone of A star, the range of distances where liquid water can exist on a planetary surface, is a concept familiar to anyone who follows exoplanet science. But there may be an analogous concept at the galactic scale. A galactic habitable zone, a range of distances from the galactic center where conditions are favorable for the emergence and persistence of complex life. Too close to the center, and the radiation environment becomes too intense, gravitational perturbations too frequent, and supernova rates too high for stable planetary systems to survive over the billions of years required for biological complexity to develop. Too far from the center, and the chemical enrichment of the interstellar medium may be insufficient to produce rocky planets with the heavy elements that biochemistry requires. The solar system's position at roughly 26,000 light-years from the galactic center places it comfortably within the range most commonly proposed for the galactic habitable zone. We are far enough from Sagittarius A star to be shielded from its violence, but close enough to the galactic disk to benefit from its chemical richness. This is not a coincidence in the mystical sense. It is a consequence of the same physical processes that make the galactic center so hostile. Stars near the center form in an environment dominated by the black hole's gravity, bathed in intense radiation, and subject to frequent dynamical disruption. Planets that form around those stars face continuous, existential threats. Stable orbits are harder to maintain. Sterilizing radiation events are more frequent. The galactic center is likely not devoid of planets, but it is an environment where the odds are stacked against the kind of long-term planetary stability that life, as we understand it, requires. The 26,000 light-years between Earth and Sagittarius A star is therefore not merely a distance. It is a buffer, a margin of safety that allowed a small rocky planet orbiting an average star in an outer spiral arm to remain undisturbed for 4.5 billion years, long enough for chemistry to become biology, for single cells to become multicellular organisms, for neurons to wire themselves into brains capable of building telescopes and pointing them at the very source of danger from which distance had protected them. We are products of the quiet part of the galaxy, and the quiet part of the galaxy exists only because the violent part is far enough away. But here is the thought that sits at the bottom of this entire story, the thought that makes it hard to accept not as a scientific finding but as an existential fact. The quiet part and the violent part are the same galaxy. They are not separate systems. They are not independent structures that happen to coexist. They are regions of a single gravitational entity, connected by the same spiral arms, orbiting the same center of mass, bound by the same dark matter halo. The stars you see overhead on a clear night are members of the same galaxy that contains the supermassive black hole, the screaming S-cluster stars, the invisible swarm of stellar mass black holes, the echoing X-ray eruptions, the magnetically spiraling accretion flow. When you look at the Milky Way, you are looking at all of it simultaneously, the peaceful suburbs and the violent core, compressed into a single band of light by the accident of viewing geometry. This is why the discoveries near Sagittarius A star are hard to accept. Not because they are scientifically controversial, they are not. The evidence is strong, multi-wavelength, independently confirmed, and grounded in physics that has been tested across the observable universe. The difficulty is that they force a revision of something more personal than a scientific model. They force a revision of how you relate to the galaxy you live in. The Milky Way is not the serene, unchanging backdrop that human culture has always treated it as. It is a dynamic, violent, evolving system whose center operates in a physical regime so extreme that it has taken the most powerful instruments ever constructed, working across decades, to even begin to characterize it, and that center is not somewhere else. It is not in a distant galaxy or a theoretical simulation. It is the gravitational heart of the structure that contains the Sun, the Earth, and every human being who has ever lived. The hard-to-accept truth about Sagittarius A star is not that scientists found something strange near it. Strangeness, in astrophysics, is routine. Black holes are strange. Neutron stars are strange. The cosmic microwave background is strange. What is hard to accept is that the center of our own galaxy is already extreme enough to make every one of these findings feel inevitable once we finally develop the tools to look closely enough. The stars were always there, orbiting at thousands of kilometers per second while humanity argued about geocentrism. The light echoes of ancient eruptions were always bouncing off molecular clouds while we built our first telescopes. The magnetic field spirals at the event horizon were always twisting while we catalogued constellations and named the Milky Way after spilled milk. None of this was hidden in the sense that it was concealed. It was hidden only in the sense that the tools to see it did not exist. The galactic center broadcast its nature continuously, in radio waves, infrared photons, X-rays, and gravitational signatures. Humanity simply lacked the receivers. Now that the receivers exist, now that the Event Horizon Telescope can resolve the shadow of the black hole, now that XRISM can read the spectral fingerprints of ancient eruptions, now that infrared instruments can track individual stars at relativistic speeds, the picture is assembling itself with accelerating clarity. And the picture is one of a galaxy whose center is not a diagram in a textbook, but a real physical environment where matter, radiation, and gravity interact in ways that belong to a category of violence the calm night sky never whispers about. Go outside tonight. Find a dark place away from city lights. Let your eyes adjust. Look up and find the Milky Way. Follow the band of light toward the constellation Sagittarius, toward the thick, bright clouds of stars near the galactic center. You will see nothing unusual. No flares, no shadow, no hint of the 4 million solar mass black hole that anchors the entire galaxy. No trace of the stars whipping around it at percentages of light speed. No echo of the 10,000-fold eruptions that lit up the molecular clouds within the span of human civilization. No sign of the 25,000 invisible stellar mass black holes grinding through the stellar population in the central parsec. Just light. Soft, ancient, beautiful, quiet light. That is the lie the Milky Way tells every night. Not a deliberate lie. A lie of distance and dust, and the limitations of human eyes. The galaxy does not hide its center out of malice. It hides it because 26,000 light-years of intervening material absorbs the visible evidence, and human perception was never designed to see through it. But the evidence is there, encoded in wavelengths we cannot see, in motions we cannot feel, in timescales we cannot directly experience. The instruments see it, the data confirm it, the physics demands it. The center of the Milky Way is a place of profound astrophysical violence, and we live in a galaxy that has been harboring that violence for as long as the galaxy has existed. What scientists found near Sagittarius A star is hard to accept because it is not about a discovery at the edge of the unknown. It is about a discovery at the center of the known. It is about the place where the Milky Way keeps its heart, and the realization that the heart has been beating with a ferocity that the rest of the galaxy, and every living thing in it, has been quietly sheltered from for billions of years. The calm you see when you look up is real, but it is not the whole story. It is the margin, the buffer, the accident of distance that allowed you to exist long enough to learn what lies at the center. And what lies at the center is already far harder to emotionally accept than most people will ever realize, because it means the galaxy you call home has always been, at its core, a far stranger and more violent place than its gentle light will ever let you see.